The title of this presentation is Speckle Tracking Analysis of Fetal Ventricular Function in Growth-Restricted Fetuses with Absent or Reversed Diastolic Flow of the Umbilical Artery. I would like to thank my colleagues, Dr. Edgar Hernandez Andrade and Dr. Roberto Romero of the Perinatology Research Branch of the Eunice Kennedy Shriver National Institute of Child Health and Human Development for their collaboration with this study. The purpose of this study was to evaluate right and left ventricular function in fetuses with severe growth restriction and absent or reversed diastolic flow of the umbilical artery, and compare results from those with perinatal deaths and those who have survived the neonatal period. Let's now review the methods used in this study. First, let's examine speckle tracking analysis. Speckle tracking analysis evaluates movement of the endocardium during the cardiac cycle. Using the right ventricle as an example, the user simply places the cursor at the base of the ventricle, points 1 and 2, and at the apex, point 3. This then activates the software analysis to compute the endocardial borders at end systole and end diastole. Once the yellow lines identify the contour of the endocardium, the user can adjust each point of the contour as needed. What does speckle tracking mean? The endocardium of each ventricle is composed of digital pixels. The image on the left illustrates a portion of the endocardium of the left ventricular septum, which has pixels of various shades of gray in intensity, represented by the green box. These pixels, or speckles, located at the different locations along the endocardial border, can be tracked by computer software as the ventricles contract. Let's now do a deep dive and examine what is being done by the software. From these thumbprints of pixels, 24 equidistant points on the lateral wall and 24 points on the septal wall are identified, represented by the red dots on the graphic on the right. For example, point 1 is at the base of the lateral wall, and point 24 is located at the apex of the lateral wall. Point 26 is opposite point 24 at the apex of the septal wall, and point 49 at the base of the septal wall is opposite point 1 of the lateral wall. Data from the locations of these points from each side of the chamber are used for the computations of the width of 24 segments, distributed from the base to the apex of the ventricle, as well as the length. The 24-segment end diastolic and end systolic widths of the right and left ventricles is a new concept. The graphic on the right illustrates the 24 segments, with segment 1 located at the base, segment 12 located at the midsection of the ventricle, and segment 24 located at the apex. In addition, the length of each chamber can be computed. These end diastolic and end systolic measurements form the basis for a number of derived measurements that were used in this study to compute global, longitudinal, and transverse contractility of the right and left ventricles, as well as left ventricular function. This graphic illustrates the three types of right and left ventricular contractility: global, transverse, and longitudinal, that will be described in this study. In addition, a measurement of left ventricular function can be computed using Simpson's rule, in which the volume for each of the 24 segments is computed and summed to derive the end diastolic and end systolic volumes for the left ventricle. This can only be done for the left ventricle because the chamber is shaped like a bullet, while the right ventricle is shaped like a triangle. Let's now examine the study subjects. The study consisted of 49 fetuses with absent or reversed end diastolic flow of the umbilical artery. Group 1 consisted of 13 fetuses who experienced a perinatal death. Of the 13 deaths, 6 occurred in utero and 7 in the neonatal period. Group 2 consisted of 36 fetuses who survived the neonatal period. The gestational ages for Group 1 were between 21 and 32 weeks, and Group 2, 23 to 32 weeks. Let's now review the statistics that were used in the study. There were two types of statistical analyses used in the study. First, z-score measurements between 200 control and 49 study subjects were compared using the t-test. The z-score is computed by obtaining the measured value of a cardiac measurement from the study fetus, then subtracting the expected mean value from a normal control group, and then dividing the value by the standard deviation from the control group. Second, the percent of fetuses with abnormal z-score values less than -1.65 or the 5th centile, or greater than 1.65 for the 95th centile, were determined and compared using the Fisher's exact test. Let's now examine the results of the study. Let's first examine global ventricular contractility. Global contractility is measured using the fractional area change. It is computed from the end-diastolic and end-systolic areas for each chamber using the equation on the screen. Using the t-test to compare z-score values from the 49 study fetuses with 200 controls, both the right and left ventricular fractional area change z-score was significantly less than the 200 normal controls. When comparing those with a perinatal death and those who survived the neonatal period, there was no significant difference in the percent of fetuses with an abnormal right and left ventricular fractional area change below the 5th centile. Next, let's examine the 24-segment transverse fractional shortening. The transverse fractional shortening is computed by subtracting the end systolic width from the end diastolic width and dividing the result by the end diastolic width. This is done for all 24 segments. The left ventricular mid-chamber segments 10 to 16 were significantly less when compared to the 200 control fetuses, as were segments 17 to 24 located in the apical portion of the left ventricular chamber. There were no significant differences in the percent of fetuses with abnormal transverse fractional shortening less than the 5th centile for all segments of the left ventricle between fetuses with a perinatal death and those who survived the neonatal period. The z-score values for the right ventricular mid-chamber segments 10 to 16 were significantly less when compared to the 200 control fetuses, as were segments 17 to 24 located in the apical portion of the right ventricular chamber. There were no significant differences in the percentage of fetuses with abnormal transverse fractional shortening for all segments of the right ventricle between fetuses with a perinatal death and those who survived the neonatal period. Next, let's examine longitudinal ventricular contractility. This measures movement of the base of the ventricle towards the apex of the ventricle during systole. There are 5 different measurements that examine longitudinal contractility. The first 3 measure the length of the endocardium during systole and diastole and are called global strain, lateral wall strain, and septal strain. The 4th measures movement of the base towards the apex and is called basal apical fractional shortening. The 5th is the annular plane systolic excursion and measures the distance the annulus moves towards the apex during systole. These are the results for the basal apical length fractional shortening. Only the right ventricular basal apical length fractional shortening was significantly less than the 200 control normal fetuses with a mean centile of 7.4%. This graph illustrates the percentage of fetuses with an abnormal basal apical length fractional shortening less than the 5th centile for the right and left ventricles. When comparing those with the perinatal death and with those who survived the neonatal period, there was no significant difference between the groups. This represents the endocardial strain of the entire endocardium as well as the lateral and septal walls. All strain measurements for both chambers were significantly different than the control fetuses, with mean centiles ranging from 67.2% to 96.5%. The graph illustrates the percentage of fetuses with an abnormal longitudinal strain greater than the 95th centile for the right and left ventricles. When comparing those with a perinatal death and those who survived the neonatal period, there was no significant difference between the groups. Similarly, there were no significant differences in the percent of fetuses with abnormal wall and septal strain between those with perinatal deaths and those who survived the neonatal period. This represents the annular plane systolic excursion. The RV and LV lateral wall and LV septal wall annular plane systolic excursion were significantly less than the control fetuses, with values ranging between 10.7% and 12.5%. The graph illustrates the percentage of fetuses with an abnormal annular plane systolic excursion less than the 5th centile for the right and left ventricles. When comparing those with the perinatal death and those who survived the neonatal period, there was no significant difference between the groups. Next, let's examine left ventricular function. This represents the left ventricular function derived from measurements of the end diastolic and end systolic volume derived using Simpson's rule. The stroke volume, cardiac output per kilogram, and the ejection fraction were significantly less than the controls. The value ranged from 2.3% for for the ejection fraction to 22% for the stroke volume. There were no significant differences in abnormal left ventricular function measurements between fetuses with a perinatal death and those who survived the neonatal period for stroke volume, cardiac output, and cardiac output per kilogram. However, for the ejection fraction, there was a significant difference between those with perinatal deaths versus those who survived the neonatal period. Conclusions. 1. There are significant differences for almost all z-score measurements between study and control fetuses. 2. The measurement that had a mean z-score value of greater than 1.65 was RV global strain. 3. The measurements that had mean z-score values less than minus 1.65 were the RV fractional area change and the LV ejection fraction. 4. There were no significant differences in the number and percent of fetuses with perinatal deaths versus neonatal survivors for all measurements except for the LV ejection fraction, which was significantly more frequently abnormal in those who had a perinatal death. 5. An abnormal LV ejection fraction may be used to identify those fetuses at increased risk for perinatal death. Thank you for your thoughtful participation.